8 is, oh, no sprinkles. Again, this may be the 4th day, no sprinkles in the kitchen. I think I already said that. April the 3rd, 2025. This guy said he pulled these numbers out of the top of his head, something to that effect. Look at the numbers he picked. Hitchhiker's Guide number, and then my number nearly. Amazing. 6 times 6, 36. Plus 6, 4 equals 42. Amazing. Something's going on. Another miracle.
But that's the issue of choice. It works, but it also creates ridiculous paradoxes. So, is it right? Well, it all starts with the issue of choice. Try this. Choose a number. I can just pluck a random number from my head, like 37 or 42, but that is the human brain.
Nothing's just. Just is a false word. Let's see what he's been saying.
There is a rule in mathematics that is so simple you would think it obviously must be true. But if you accept it...
I said rule is a false word. Now I'm going by emotion when I choose these false words.
You find there are now some line segments that have no length. A sphere, without adding anything to it, can be turned into 2 identical spheres. 100+ years of mathematics has been built on this axiom. It seems intuitive and it works, but it also creates ridiculous paradoxes. So, is it right? Well, it all starts with the issue of choice. Try this. Choose a number. I can just pluck a random number from my head, like 37 or 42, but that is the human brain at work, not a mathematical process. In math, you can't truly pick things at random because formulas always the same result, which is why computers have true random number generators. Instead, they usually run an algorithm on your current local time to generate numbers that appear random. So, if we can't pick randomly, how do we select anything in math? Well, the only way is to follow a rule of some sort.
There's no
So, a rule could be, always choose the smallest thing. For example, if we're looking at whole positive...
No such thing as random, so just rule, nope. Hold on, let's see what he said.
Pluck a random number from my head, like 37 or 42, but that is the human brain at work, not a mathematical process. In math, you can't truly pick things at random because formulas always give the same result, which is why computers...
Exactly, that's why there's no such thing as random.
...don't have true random number generators. Instead, they usually run an algorithm on your current local time to generate numbers.
Exactly what he's talking about. I learned in electrical engineering class many years ago. It goes by the zeros and ones from your power outlet, from the power. Exactly what he's talking about. There's no such thing as random.
That appear random.
I've never heard anyone actually say that, except for the that one lecturer a long time ago. I don't even know if it was in the textbook.
Don't have true random number generators. Instead, they usually run an algorithm on your current local time to generate numbers that appear random. So, if we can't pick randomly, how do we select anything in math? Well, the only way is to follow a rule of some sort. So, a rule could be, always choose the smallest thing. For example, if we're looking at whole positive integers, the smallest is 1. For prime numbers, it would be 2. Easy. But what about the real numbers? That's any number, positive, negative, whole, fraction, even irrational, like pi or the square root of 2. Now try to choose the smallest one. It's impossible. The real numbers stretch off to negative infinity. Even if we try to fix our rule by making it super specific, like choose the smallest number after 1, we still get stuck. There's 1.01, then 1.0001, then 1.000001, and... This was just an assumption. Nowhere...
Incredible. I've been right all along, that means.
The mathematical rulebook was this explicitly permitted. And math is built on rules, specifically axioms. Axioms are simple statements we accept as true.
Principle, false word.
Formalized into something that holds up in a system of proof. A new axiom that said making all of those choices was possible. He needed the axiom of choice. The axiom of choice can be said in the sense that if you have infinitely many sets, and each set is not empty, then there is a way to choose one element from each of the sets. For finite sets, this seems obvious. Just go set by set and pick something. Even for infinite sets, it's easy if there's a clear rule, like always choose the smallest thing. But sometimes there is no natural rule. In those cases, when you're choosing from infinitely many sets, including the uncountable ones, you need the axiom of choice. We can't say how we're choosing, but the axiom makes all of these choices all at once. The axiom doesn't allow you to say which element you've chosen, only that infinitely many choices are possible. So how does this new axiom enable us to well-order the real numbers? Zermelo uses the axiom of choice to choose a number from the set of all real numbers. He places this number, let's call it x1, into a new set R. The axiom then allows him to choose another number from the subset of all reals minus the one taken out. He calls this number x2 and places it as the next number in his set. And he keeps doing this, taking the chosen number and placing it next, x3, x4, x5. Now, it feels like he's choosing these numbers one at a time, but in reality, the choices are made from all possible subsets at the same time. As Zermelo indexes each number with the natural numbers, at first it might seem like he'd run into a problem, because the natural numbers are only countably infinite, whereas there are way more reals, so he should eventually run out of labels. But we can count beyond infinity. We did it earlier when we counted past positive infinity to get the -1, -2, and so on. So we just need a new set of numbers that extends past the naturals. Call the next number omega, then omega plus 1, omega plus 2, and so on.
The most overused false word is just. So there's a ton of false words. I already said it in the beginning. I'm not going to repeat it if you hear it again.
Omega numbers are not bigger than infinity. They just come after infinity. They don't tell us how many things are there, but they do tell us their order. So the next number we pull out, we'll label it x omega, then x omega plus 1, x omega plus 2, and so on. This will continue until we match the size of the real numbers and our original set is empty. Now, every real number is in our new set. There is a first number, x1, and every subset also has a first number. And just like that, we've successfully well-ordered the real numbers. This order looks nothing like our familiar order. A billion could come before 0.2, but with this process, we can prove that a well-ordering exists. And more than that,
Prove, another false word, prove.
we now have a way to resolve our issue of how to choose mathematically. We can't pick a smallest real number, but now we can pick a first real number, our starting point. And we can do this for any set, meaning all sets can be well-ordered, no matter the infinity. So Cantor's well-ordering theorem and Zermelo's axiom of choice are equivalent. Cantor was so relieved. Zermelo had proved the well-ordering theorem and well-ordered the real numbers all in under a month. Zermelo took something mathematicians had unknowingly relied on for decades and turned it into a formal axiom. He showed that understanding math isn't just about numbers, it's about the logic behind them. And lately, I've been trying to do a similar thing, but with AI, where I'm trying to understand the logic behind how models like ChatGPT work. And if you also wanted to learn how generative AI actually works, well then you can do that with today's sponsor, Brilliant. Brilliant has just launched a great course that breaks all of this down with interactive visuals, which is exactly what I love about Brilliant. And the course builds your intuition for the math and logic behind AI, exploring how models are trained to spot patterns, generate images, and even whip up a song. Strongest riding through the sky. Brilliant has thousands of interactive lessons in math, science, programming, technology, and VR, all designed to sharpen your thinking and problem-solving skills. And since each lesson is bite-sized, you can jump in anywhere, anytime, on your laptop, or even on your phone. So to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/veritasium. Click that link in the description, or scan this handy QR code. And if you sign up, you'll also get 20% off their annual premium subscription. So I want to thank Brilliant for sponsoring this video, and now back to the axiom of choice. The axiom of choice may have been a new idea, but its use was anything but. Zermelo scanned dozens of papers from other mathematicians and realized they had also been using the axiom all along, even those who had criticized Cantor's work. It just goes to show how unintuitive it is that it's even an axiom. People have been using it for like a decade. Unknown. This almost seems too obvious. Zermelo's proof didn't actually construct a well order, he just said what must exist. But can something exist if we can't actually build it? His proof also used an uncountable number of steps. Was that even allowed? Some mathematicians argued proofs should be finite. Others accepted infinity, but only the countable number. And then things got worse. When mathematicians played around with the axiom of choice, it created disturbing results. One of the first came from Giuseppe Vitali in 1905. Vitali used the axiom of choice to build a set of numbers that shattered our idea of what it means for something to have length. So what Vitali does is he takes every real number between 0 and 1 and assigns it to one of an infinite number of bins. Let's call these bins groups. So we want each real number to end up in exactly one of our infinite bins. So how does he do it? Well, let's say we have two numbers, x and y. If their difference, x minus y, is equal to a rational, that is, one integer divided by another integer, well then both x and y will go into the same bin. But if we have two other numbers, let's say p and q, and their difference is not irrational, so it's an irrational difference, well then those two numbers will go into separate bins. So let's do some examples. If this is 3/4 minus a half, then we get a quarter, and so both 3/4 and a half will go into the same bin. In fact, you can see that all rational numbers from this span 0 to 1 will all end up in the same group. Now, if you have irrational numbers, well, it's not clear whether they will go into the same bin or not. Because, for example, if we have the number √2/2 minus, say, √2/2 minus a quarter, well, then that does have a rational difference, even though each of these numbers is irrational. So these two numbers will go into the same group. But if we have irrational numbers √2/2 minus √2/3, well, that gives an irrational difference. So √2/3 will have to go into a different bin, and it will be joined by all of the numbers it has a rational difference from. And in this way, you can assign each real number to exactly one of these bins. Next, I'll use the axiom of choice to reach into each group and select exactly one number to be a representative of the group. So we can pull out 3/4 from the rational group, √2/2 from this group, √2/3 from that group, and so on. So of course, because we're using the axiom of choice, you don't actually know what that representative number is, just that you have one. So we can write it down like this. We have these representatives from each group, and together they form the Vitali set. You can visualize this set as a collection of points between 0 and 1. Next, Vitali makes infinite copies of his set, and each one he shifts by a different rational number between -1 and +1. So if you think about what that does, it's going to move each representative number to be at the position of every other number in its group. If we just had the one rational number that we plucked out as a representative from the rational group, now we're going to shift it by every possible rational number between -1 and +1. If the size of the Vitali set is 0, you add it up, then you want to play it. If you choose that the fifth axiom doesn't hold, so there are no parallel lines, then you're playing in spherical geometry. If you choose one parallel line, you're playing in flat geometry. And if you choose more than one parallel line, then you're playing in hyperbolic geometry. All of these geometries are valid. It just depends on the math you want to do. And it's the same for the axiom of choice. The axiom of choice can be either proven or disproven from the other axioms. So as long as the other axioms are consistent, adding choice won't lead to any contradictions. Paul Cohen was awarded the Fields Medal 3 years later for his groundbreaking result, as well as his other work in set theory. And after Gödel and Cohen's work, most of the debates about the axiom of choice died down. In the end, what the hell is going on is that it's up to you whether you want to choose where the axiom of choice will be part of your system or not, and basic consequences of either having it or not. Despite the counter to choose where the axiom of choice will be part of your system or not, and basic consequences of either having it or not. Despite the counterintuitive results created by the axiom of choice, like non-measurable sets and infinite duplication, it is incredibly useful. Choice allows mathematicians to replace lengthy explicit results created by the axiom of choice, like non-measurable sets and infinite duplication. It is incredibly useful. Choice allows mathematicians to replace lengthy explicit proofs with more concise arguments. By proving statements in the finite case, many proofs.
Proof is another false word. I think I already said that. No, I haven't. Proof. Yeah, proof.
Can be extended to any infinite case in just one line. This reduces proofs.
Case, another one.
It would have been 20 pages to just half a page. And the axiom of choice doesn't just make math easier, it is essential to some proofs. There are many theorems where the general case can be proven without using choice some way. Now, some mathematicians still prefer proofs without choice. Even if it's harder, the proof has to be spelled out step by step to generalize to infinite cases of this provides.
Generalize, another false word. So many. Okay.